Hi, everybody. This is going to be a video on the test for convergence. This test has already come up in other videos, but it probably doesn't hurt to have more examples. So I'm going to go ahead and state the test for convergence, and then I've got, looks like 4 examples I'm going to do. So here is the test for divergence. Right, and one important thing to remember here, why is that so, there, that looks a little better. One important thing to remember here, this test can only tell us if something doesn't converge. It doesn't tell us when something does converge, okay? So the test is just this. If the limit as n goes to infinity of a sub n, so if we have a sequence whose limit is not 0, anything other than 0, which includes a number that's not 0, or a limit that doesn't exist, like infinity, or something that just bounces around without ever settling down towards one number. If any of those cases are true, the only case that this doesn't apply is if it does equal 0. Otherwise, then the series of that sequence, right, the series whose terms are that sequence, diverges, right? Again, it cannot tell us when something converges, but it can only tell us when something diverges. So let's do a couple of examples. Let's start with the series. We will test, what's my example? Let's take the series n equals 0 to infinity, 1 to infinity of n squared minus 1 over n times n plus 1. Right? So what we would do to compute this, to use this test, is we look at the sequence, the limit of the sequence made of the terms of this series. Right, and there's a few ways you might do this. We could do some algebra. N squared minus 1 is n plus 1, n minus 1. So this is just the limit as n goes to infinity of n minus 1 over n. You could use our limit laws with various things. In my class, we taught there's a little rule when you have rational functions. If the polynomials have the same degree, then the limit is just the quotient of the leading coefficients. So in this case, they're both degree 1, they're both linear. We have a leading coefficient of 1 over 1. This limit is 1. And clearly, 1 is not equal to 0. Right? Which means the series n equals 1 to infinity of n squared minus 1 over n times n plus 1 diverges. Right? Which is another way of saying it doesn't sum up to anything. In this case, it'd be pretty easy to argue, since the terms are going to be positive once we're bigger than 1 for n, it's going to keep growing in an infinite way, right? We can make it as large as we want. But all we needed to know for this is that it diverges, and we know it diverges because the limit of the terms is not 0, okay? Let's do another example. This one's a little bit trickier. N equals 1 to infinity of n times the sine of pi over n. Right? This is a tricky, this is an interesting one to look at. We want to decide what's going to happen. Let's notice a couple of things. What's going to happen to our terms? Well, let's just write down our test for divergence, right? We want to test the series or the sequence, right? The sequence made up of these terms. This part of this is growing, right? As n goes to infinity, n goes to infinity. So the front half of this, the first factor, n, is just getting larger and larger and larger. On the other hand, we have sine of pi over n, which means the argument of sine, the thing we're plugging into sine, pi over n, is getting smaller and smaller and smaller. Well, as we put inputs into sine that are getting closer and closer to 0, we end up with something closer and closer to 0. Sine of 0 is 0. As we get close to 0, it becomes 0. So what we're ending up with is something whose limit is infinite times something whose limit is 0. And as we should remember, 0 times infinity is not 0, it's not infinity, it's indeterminate. We don't know anything about this limit from this alone, right? The fact that one gets really large and one gets really small. They're competing with each other, right? N is trying to make it big, sine of pi over n is trying to make it small. And we have to figure out which one is winning. So I'm going to write this, I'm going to use, remember, I'm going to consider the function f of x equals x times sine of pi over x. This is a function equal to this sequence. It's just more comfortable for me to look at it in terms of x because I'm thinking about it as a function right now and taking its limit. And let's take this limit as x goes to infinity of x times sine of pi over x. Same argument there, we've got infinity times 0. We might remember a trick for this kind of indeterminate form. So I've rewritten x times sine of pi over x as sine of pi over x times 1 over x, right? Putting 1 over x in the denominator is the same as having x in the numerator as long as x is not 0, and it's not. We're talking about heading towards infinity, so we're fine to do this. So let's think about what we can do here. This, we already said the limit here is 0. The limit in the denominator is also 0, which means we have something that is perfect for L'Hopital's rule. Pardon me. So we've got a limit as things go to infinity that are 0 over 0. We can use L'Hopital's rule, which tells us that we can take the derivative of the numerator and the denominator separately. The top has a chain rule, so we're going to have the limit as x goes to infinity. The derivative of sine is cosine. We leave the inside alone. And then the derivative of this is pi times x to the negative 1, is going to be, let's put it here, negative pi x to the negative 2. Okay, so that's just a little chain rule. This is x to the negative 1. That's another way to think about it. Its derivative is negative x to the negative 2. Right. Now we see a factor of x to the negative 2 in negative x to the negative 2 in the numerator and the denominator, so I can cancel those two factors. And it also cancels that negative because I've got negative in both. And I've got the limit as x goes to infinity. I've got a constant pi and a cosine of pi over x. Well, as x goes to infinity, pi over x becomes 0. Cosine of 0 is 1. So if you think all the way back to the chapter on limits, I believe it's in chapter 2, we have this idea that when we have continuous functions, we can take the limit of the thing inside, and the limit of their composition will just be cosine of the limit of this, which in this case, cosine of the limit of this is cosine of 0 is 1 times the constant pi. Our limit is pi. And of course, pi is also not equal to 0, which means the limit of this thing is pi, which is not 0. So the series n equals 1 to infinity, n times sine of pi over n diverges. Okay. Right. So again, divergence test can tell us when something diverges. And since the terms do not go to 0, the series diverges. Okay, couple more examples. Let's see. So I want to do 2 quickly. So let's look at the following. N equals, what do I want here? Well, let's do 0 to infinity. And we'll have n squared over e to the n cubed. That's an n cubed, sorry, it's not, I should have written this a little bigger. Okay, so we want to test this series. And we will do it in the exact same way. I'm going to skip the computation just so that, and I'll just let you know, this is an example of L'Hopital's rule. We just did one with L'Hopital's. You can do L'Hopital's on this twice. Some of us may have noticed in the past that whenever we have an exponential versus a polynomial, the exponential tends to win, but the exponential will win. And so in this case, after several applications of L'Hopital's, you will find the limit is 0. Let's just leave that there for a moment. And let's look at this series. The limit as n goes to infinity of 1 over n is a simple one, is also 0. Okay? The test for divergence tells us nothing about either of these. The fact that the terms are 0 does not mean it converges, right? Not being 0 means it diverges. The limit of the terms of the sequence being 0 doesn't imply it converges. And in fact, I showed you this one in an earlier video. This one does diverge. This one turns out to converge. I will show you this one in a later video when we get to the integral test. We will do this series. But suffice it to say, I have an example here. The important takeaway is both cases go to 0. One diverges, one converges. And so that 0 is, doesn't tell us anything. Okay, that is our test for divergence, and that's it for this video. See you in the next one.